Hey, welcome to section 11.3, the third section of chapter 11 for our Algebra 1 Math 8A course. And today we're going to be talking about simplifying rational expressions. So we talked about what a rational function is, what a rational expression is, something like this, where it's a ratio, it's something over something. Today I want to start with the question, what does this equal? Well, hopefully you can tell without needing me to teach you this that anything divided by itself is 1. Right? Okay, so we just simplified a rational expression. We took a rational expression and we simplified it, and what we basically did is we simplified it by taking this and canceling out with itself. It's just matching and scratching, just with expressions. Now, I do want you to be careful when you think about this. When you are simplifying a rational expression, let's say it was x plus 2 over x plus 3. Sometimes you cannot simplify this. Sometimes the simplest version of it is just itself. Don't think that just because we scratched x's and minus 1's out here that we can scratch x's here. You can't scratch part of a binomial without scratching out the entire binomial. And since this binomial doesn't match that binomial, you can't match and scratch. There isn't a match, and that is already in simplest form. Hopefully that kind of makes sense, but the main idea is don't try to match and scratch parts of polynomials. You have to match and scratch matching polynomials. Speaking of which, my second challenge for you today as you watch this video is, what does this rational expression equal? The difficulty. I'm not allowed to just cancel the x and the x, and the minus 1 and the 1, and unlike this one over here, these actually don't quite match. So what am I going to do? Just give up and say it's already in simplest form? Haha, no. The answer to this is -1. That whole rational expression is an explanation of that, because this is kind of an important little trick that you're going to need to know when you're dealing with rational expressions and polynomials and binomials, trinomials, and all that kind of good stuff. What I want you to see is specifically that 1 minus x equals -1 times negative. Take a second and soak that in. 1 minus x equals -1 times -1, -1 times x. Are we okay with that? I hope so. Another way that you could write this would be instead of -1 plus x, couldn't we write x minus 1? Maybe I'm starting to see what Mr. M's point is going to circle around to here, because if I took this whole rational expression, I started off with this, correct? And what I ended up with was x minus 1 on the top still, right? But on the bottom, I was able to rewrite this binomial as this binomial here eventually. And now I have an x minus 1 and an x minus 1, and guess what happens? This x minus 1 cancels with this x minus 1, and what am I left with? It would be 1 over -1, but that's -1, isn't it? Okay, so the moral of the story here is when you have two binomials and they're both minuses, they both have a minus in the middle, they're both differences, but they're reversed order from each other, you can just match and scratch. But instead of matching and scratching and leaving a 1 behind, they match and scratch and leave a -1 behind. That's a nice little trick, huh? Yay! Okay, next I would like you to tell me how could we simplify the following rational function? Not function, rational expression. Let's say I have y squared plus 9y minus 10 over 2y plus 20. I can't match and scratch yet, because even though I've got a y here and a y here, I can't match and scratch this y and this y. I can only match and scratch matching expressions, matching polynomials, matching binomials or trinomials. And this trinomial does not match with this binomial at the bottom. So in order to simplify this, what I need to do is factor, 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 factor. I'll start with the bottom. The bottom, it's easy to factor out a 2. Okay? The top is a trinomial, and we're going to have to remember factoring trinomials. That's right. We didn't leave that behind in chapters 8 and 9. We still need to know how to do this. How do you factor a trinomial? Let's go back to magic numbers. What times what makes negative 10, but also adds up to 9? In this case, it is 10 times negative 1 and 10 plus negative 1. So my magic numbers are 10 and negative 1, and we have successfully factored this trinomial. Now I can match and scratch. That makes sense? Hopefully you can see that. And now I can simplify this rational expression. And I think we would all agree that I did successfully simplify that. This is a simpler way of writing the expression compared to what we started with. These are equal, they're equivalent, but this is a simpler version. So we just simplified a rational expression. Yay, good for us, nice work. Let's try another one. Let's try to simplify x squared minus 9 over x squared minus x minus 12. And if you want to go ahead and pause this video right now and try that on your own, you can do that. Otherwise, just stay tuned and I will walk you right through it. So we're going to factor, factor, factor. Factor the top. Ooh, that's a difference of squares. Remember what to do here? Remember that little trick of factoring? What do we got on the bottom? We're going to do some magic numbers. Okay, I think 4 and 3, 4 and 3, but this has got to be a negative 4 plus 3 and a negative 4 times 3. So on the bottom I've got x minus 4, x plus 3, a positive 3 and a negative 4. And again, can I match and scratch? I sure can. This and this match and scratch. And so my simplified version is... This is kind of fun, simplifying rational expressions. I like matching and scratching. It gives me some kind of weird sense of satisfaction. Sorry, did that disturb you to know that? Maybe you share my weird math satisfaction, but we're going to keep going. 3y minus 27 over 81 minus y squared. And again, we're just simplifying. I want to take this rational expression and rewrite it in a simple form. So we're going to factor again. The top, I'm just going to factor out a greatest common factor. Everybody okay with that? Good. The bottom is a difference of squares, 9 and y. So it's going to be 9 plus y, 9 minus y. And this gives us a little bit of a conundrum. The 3 doesn't have anything to match and scratch with. The y minus 9 doesn't match with this or this. So wait a second. Remember that little trick I showed you? Y minus 9, 9 minus y. They do match and scratch, but what are they going to leave behind? They're going to leave a negative behind. So that is my answer. Fun. Yes. Okay. I think we got it. We got the hang of this. All right. Now, remember, with rational expressions, there are things called excluded values. We talked about that. Excluded values. When we were looking at graphing these kind of rational functions, excluded values are what can't x or y or z or whatever that variable equal? So for this particular one, the excluded value here would be y cannot equal -9, because that would make the denominator 0, and you can't divide by 0. However, we have to be careful with excluded values, because if we look at the original function, y can't equal 9 either, because then I would have 9 minus 9 right here. And then I would have 9 plus y times 0. So a positive 9 would also be an excluded value for this rational expression. So if you're finding excluded values, find excluded values before you simplify, not after you simplify. That's the moral of the story there. Okay, easy enough. Should we try one more excluded values? Sure, why not? What are the excluded values of the following rational expression? In order to know what a can't equal, I'm going to have to factor. But I don't need to even really worry about factoring the top, and I can't anyways. I just have to factor the denominator, because for excluded values, we only really care about not making that denominator 0. All right, so I believe this is 4 times 2, and this is 4 plus 2. So I've got a and 4 and a and 2. Everything's positive. That makes it easy. So what are my excluded values here? A cannot equal -4 or -2, because either one of those would make a 0 on the denominator, and that is illegal, impossible. Finding excluded values, still important, still pretty easy. All right, I got another problem for you here. This time, I'm going to give you a function. Okay, I'm going to give you a function. It's going to be a rational function. X squared plus 2x minus 15 over x plus 1. And here's what I want you to do with this. I want you to find the zeros of the function. So we have to remember, what the heck is a 0? What is a 0? The 0 of a function is where the function, right? Where the function equals 0. So how do we find the value of, or the function, the 0 of a function like this? One thing that we could do is you can find that on a graph. Remember, zeros appear as x-intercepts on a graph. So one thing I could try to do here is use Desmos, show you a picture of this graph. Okay, so here's the function. I just typed it in. I put it in Desmos. Look at that interesting graph that this makes. I don't know that we've seen a graph that looks like that yet, but okay, kind of cool looking. It looks like it has 2 different zeros. Where are they? I don't know. Oh, by the way, it has a vertical asymptote right here. Doesn't have a horizontal asymptote, does it? Interesting. Okay. Kind of hugging that y-axis, but as we zoom in, okay, there we can see where our zeros are. Our zeros are at -5 and +3. Everybody see that? -5 is one 0, and +3 is another 0. But do you have to use Desmos in order to find zeros? I don't think you do. I think we can find the zeros of this function just by doing a little bit of math. If a 0 is where the function equals 0, to find the 0, we just set the function equal to 0 and solve for x. That's all we have to do, right? So how do we do that? Well, let's see. For this to equal 0, wouldn't we just do that? Multiply? Which makes this go away, and 0 times that is 0. Basically, all we care about to find a 0 is what would make the top equal 0. So when we're finding the zeros of a function, we're kind of doing the opposite of finding excluded values or finding asymptotes. We're finding what makes the top, what makes the numerator 0, as opposed to what makes the denominator 0. Although I will just say, quick note, if we were to solve this and get x equals -1 is a 0 of the function, I would tell you, no, it's not a 0 of the function. If it's already an excluded value, it can't be a 0. It's disqualified, so to speak. But I don't think we're going to get that answer. We actually already saw that we're not going to get that answer because we saw the x-intercepts on the graph, and we just have to factor this to figure out where the actual zeros are. So what are my magic numbers? 5 and -3. 5 times -3 is -15. 5 plus -3 is +2. So what are my zeros? I have a 0 at x equals -5, and I have a 0 at x equals 3. And isn't that what we saw on Desmos when we graphed it? Yeah. Okay, so what does it mean to find the zeros of a function? It means what x values make the top, what x values make the numerator equal to 0, instead of looking for what makes the denominator equal to 0. So you are going to, in section 11.3, simplify some rational expressions where you're matching and scratching, but you're only matching and scratching like expressions, like polynomials. And you're going to be finding some excluded values by trying to find out what's going to make a denominator come out to 0. And you are going to find some zeros of functions by figuring out what makes the numerator equal to 0. But remember, excluded values can't be zeros, so be careful with that. And remember this fun little trick that we learned about how to sometimes cancel things that don't look like they're going to cancel, and how sometimes you can cancel and leave a -1 when you have a certain particular situation and scenario, such as that. All right, thanks for watching. Thanks for listening. If you have any questions, let me know. Otherwise, good luck on 11.3, and I will talk to you tomorrow.